In this video, we'll be looking at segments of circles and the equations that are associated with them. First off, let's look at the theorem that involves two chords inside of a circle. If two chords intersect in a circle, then the product of the lengths of the segments of one chord equals the product of the lengths of the segments of the second chord. In other words, if you just have two chords inside a circle, AE times EC will equal DE times EB. So you take the one part of the chord, multiply it by the other part, set it equal to one part of the chord times the other part. Now, this does not mean that the chords are congruent to each other. It just means that the product of their parts are equal to each other. Really, if you wanted to prove this, you would actually draw some lines and set up similar triangles, and then you could set up a proportion. So just understand that the sides are proportional to each other, but not that the chords are congruent. So here's how it'll look like. Two chords meet inside the circle. So part of the chord times the other part, so 12 times 5 will equal one part of the chord, 6 times the other part, which is x. So 60 equals 6x, and divide by 6. So x equals 10. So we do part times part equals part times part. Pause the video and try this one out. Let's see how you did. So AE equals 8. All of CA is 12, which makes CE 4. BE is 5, and we want to know all of BD, but first we need to find ED, so x. So 5 times x, 5x, equals 4 times 8, 32. Divide both sides by 5, so x equals, let's see, 5 goes in 32, 6 times 6.4. So all of BD will be 6.4 plus 5, 11.4. All right, this one's a little bit harder, so I want you to pause and see if you can figure out how to set this one up. All right, let's see how you did. So all of BD is 12, BE is 4. So if all of it's 12 and this is 4, that makes 8. AC is 18. So it doesn't tell me what each part is. So let's call this part, let's say x, and we'll call this 18 minus x. Because if the whole thing is 18 and this is x, then what's left is the whole thing minus that segment. So that's the setup there. So now we have 4 times 8 equals x times 18 minus x. 32 equals, now we have to distribute 18x minus x squared. So let's go ahead and move the negative x squared over so we get rid of it. So add x squared to both sides and subtract 18x from both sides because we want to get all the numbers together when there's an x squared. So 18x minus 18x plus 32 equals 0. Factoring gives you x minus 16, x minus 2 equals 0. So x equals 16 and x equals 2. So both of those work. So AE equals 16 and 2. So that time we had a factor, and we also had to determine if the whole thing's 18, then we define one as x and the other 18 minus x. All right, another theorem. If two secant segments are drawn to a circle from an exterior point, so we draw two secants, and we stop them at the edge of the circle, then the product of the lengths of one secant segment, so the whole secant segment, and its external part, so this part, equals the product of the lengths of the other secant segment, this whole thing, times the external part. In other words, the whole segment, AC, times the outside part, BC, equals the whole segment part, EC, times the outside part, DC. And once again, if we were going to prove this, we would draw some triangles, and we'd prove by AA that they're similar, and then set up a proportion and solve that way. So the main thing to see here, though, is that the whole line times the external equals the whole line times the external. So pause and try this out. Let's see what you do with this. So the whole line is 12 times the external is 3 equals the whole line, so I'm going to put in parentheses x plus 4 times the external 4. 36 equals, now we have to take the 4, we have to distribute it, so 4x plus 16. Move the 16, so 20 equals 4x, and divide by 4, so x equals 5. Hopefully you're able to get that there. Let's move on to another one. Pause this one and see what you can do with it. All right, so AB is 2, BC is 6, all of EC is 15. So whole thing, 8, times the external, 6, equals the whole thing, 15, times the external, x. So we get 48 equals 15x, and we divide by 15. So x equals 3.2. All right, moving right along to our last theorem of the day. If a tangent segment and a secant segment, so notice how now we have a tangent and a secant, are drawn to a circle from an exterior point, then the square of the length of the tangent segment, so we square this, equals the product of the lengths of the secant segment and its external part. So we have the whole tangent segment squared equals the whole secant part times the external part. So let's see what that looks like here. So the whole tangent part, 6 squared, equals the whole secant part, 5 plus x, times the outside part, x. 36 equals, distribute now, 5x plus x squared. So we're going to move the 36 over, so we get x squared plus 5x minus 36. Factor that, gives you x plus 8. I'm sorry, that's not correct. Let's see, it's going to be x plus 9, x minus 4. So x equals negative 9, x equals 4. Now, can you have a segment that's negative 9? No, so x just equals 4. All right, so pause and try this one out. All right, so the whole tangent, x squared, equals the whole secant, 7 plus 4, 11, times the outside 4. X squared equals 44. Take the square root, breaks down to 4 times 11. So 2 square root 11 is the answer for x. All right, so please make sure you practice the homework, and thank you for watching.